Hi, welcome to the Signal Path. In this episode, I want to do a review for what I would consider is essentially a new type of product category. This is the M81 system from Lakeshore Crytronics. Now, Lakeshore is involved in some pretty difficult metrology scenarios, and they've brought all that knowledge into this system. There's a lot to talk about here. This is a fairly long video, so it has individual chapters that you could go and pick the section that you want to watch, but I really wanted to dig deep and figure out exactly how it works and what we can do with it. So let's get started. So why is this a new product category? It's because it combines three particular metrology techniques under one instrument, and that allows you to use it in new and unique ways and perhaps do measurements that you couldn't do before. And I'd like to talk a little bit about that before we get to use it. So the first metrology concept is the ability to do source and measurement simultaneously. Now, we've looked at SMUs in the past extensively, and these are Keithley's, which is one of the leaders in this space. So how does Lakeshore handle such a thing? Now, the Lakeshore solution here offers some really interesting flexibility because the source and measurement voltage and current are broken out into individual modules. So we have a current measurement, single-ended, a differential voltage measurement, a balanced current source, and a single-ended voltage source. There's actually a fourth module, and that module is a complete SMU unit resembling a classical SMU four-quadrant system, which unfortunately I don't have one here. I wish I could show you that as well. Now, these are all individual connectorized, some of them with BNC, some of them with triacs with all the low noise capabilities we talked about. Now, what does it mean for these things to actually be modularized? Where is the advantage there? Now, the next important metrology concept is the idea of having remote heads. Here I'm showing an example of a sampling oscilloscope remote heads that have bandwidth in excess of 110 gigahertz. Now, you can imagine, because this is portable, you can bring this much closer to your device under test, preserving that precious bandwidth at the interface of the sampling head and the device you're trying to measure. Once the signal enters here, you only have bandwidth requirements in the front end of this module. Then it gets down converted, and this cable never carries the really high frequency signal, allowing you to have the best of both worlds, having this really tight interface between the two devices and then connecting it to the mainframe for further processing. Now, how does Lakeshore take advantage of this concept of remote head in their system? And in the Lakeshore system, every one of these modules is also a remote head, separated from the mainframe using these cables and connectors that you see over here. This is a huge advantage in situations where you care about signal-to-noise ratio or potential interferences, because you can bring your DUT super close to these modules and minimize that interface to the low noise front end of these sources and measurement devices. Now, imagine that you can also separate these from each other. I'm just stacking them like this right now, which means you can also arrange them in situations where you could not do in a fixed mainframe, bringing them really close in some unusual setups. You can see how Lakeshore has thought about this because of their extensive experience in measuring a really difficult system in cryogenic environments, for example. Now, the SMU will also have exactly the same form factor, giving you this additional capability of source and measure at the same time. Now, also keep in mind that these modules will run fairly cool because you're not doing any processing in here. You're doing signal conditioning. And once you've conditioned your signal, these cables are no longer prone to the same SNR interference because you've already conditioned everything. And everything then can be analyzed and processed and digitized inside over here, separating these functions at exactly the right place to maximize signal integrity. And the next metrology concept is the idea of lock-in amplification, essentially coherent measurement. By using a lock-in amplifier, you can generate a signal at a particular frequency away from DC and then analyze it coherently and go even below the noise of the system, not to mention away from DC, and therefore removing any uncorrelated environmental interference effects. How does Lakeshore handle this? And this Lakeshore system can not only source and measure DC signals like traditional SMUs would, it can also source and measure AC signals up to 100 kilohertz. And because the mainframe is responsible for that, it can also do coherent measurements, essentially doing lock-in amplification. And that changes the way this whole system works. Now you have an SMU with lock-in capabilities. And you can even inject the signal in the back of the mainframe and measure lock-in using externally modulated signals that is not even generating using its own module. So behaving completely like a lock-in amplifier. Now imagine all of these capabilities in one: the remote head, the SMU capability, the AC signal, and the lock-in capability all together, and the wonderful set of metrology measurements you can do with all of this. That's why I think that this is a new measurement category, because I don't believe I've ever seen all of these things combined in such a scalable platform before. There's a lot to talk about, including teardowns. So let's go. And here's the front of the Lakeshore M81 SSS system. As you can see, it has a really clean design, and all the interaction with the instrument is handled through the capacitive touchscreen. It's responsive, high resolution, and of course it is articulating. The only thing I wish it was a little bit larger, for example, going all the way over there, because there is so many useful information you'd want to display on this, especially on this 6-channel version of this. You have so many parameters that you want to perhaps look at it in quick glance. We'll talk about it when we talk about the GUI, because some improvements there potentially could help as well. Here's the soft switch there, and that's really all there is to it. This articulating front panel is really helpful to look at it at awkward angles, and I can see why they've done this, because in cryogenic environments you might have things crammed in places, and then you will be able to easily read that. Of course, there's whole thing is controllable by the computer as well, which we will take a look at, but the front panel is really nice. And in the back of the unit, unsurprisingly, we have the primary interfaces for our remote modules. In this particular case, we have 3 source and 3 measure. When we open this, we'll see how they're handled on the inside. We do also have the reference in and reference out, and this is super critical because this instrument does support lock-in, and you want to be able to do this with external signals as well, or provide an external signal. Very nice that that's included. There's a monitor output there too, and we have accessory and digital I/O for various expansions, and hopefully that's controllable with the software as well. We have Ethernet, USB, and USB-C, and the GPIB for legacy control, and of course the power input, and that's all there is to it. It's really compact. Consider how many things and how many modules you can connect to this. It's nice that they have kept the size of this as small as they have. Now looking at the front and the back of these modules, you can see that in the case of the BNC, the outer conductors are floating, can go up to 30 volts above the earth ground, and the triax, the outer conductor, is grounded, but the inner one is indeed floating. Now this is pretty important for defining various common mode voltages that we will see in our experimentation. The back of the unit does have earth ground, and the cable directly goes in there. Several LED status indicating differential single-ended measurements, and various multicolor LEDs showing the status of each of these modules. Now, the connector at the back connecting to the mainframe is really high quality, as to be expected for these good metrology connections, but the connection in the back is permanent. So it would have been nice if you had also a connectorized thing at the back. I'm not sure why they haven't done that, perhaps for cost reasons or just the fact that this interface is a little bit smaller, but these cables are, reasonably flexible, but once they all get tangled up together, it'd be nice to disconnect them from here rather than having to kind of untangle them. That could be one thing they could do in the future. Color coding the end of these would also be helpful, because when you have a lot of these, it would become difficult to figure out which one is connected to what as you're trying to connect it to the back of the mainframe. These simple usability cases would certainly help in the long run. We do have nice brackets that allows you to stack these in various places, and they're very solid once you stack them together. So I'm happy with that. They've clearly thought about how to incorporate this in a much larger measurement setup. And here is what is inside of the current measurement module. You can see it's made of 2 PCBs that simply stack on top of each other. Nice compact design over here, and they communicate using these board-to-board connectors. The main cable coming in from the mainframe plugs into this connector here on the left side, which carries power and of course signals and various other things back and forth. You can see why they haven't used an additional connector over here. Even though it would have been more convenient, it would have been a lot harder to engineer this. Now, if you want to measure really small amounts of current, well, the very first thing you would need is a transimpedance amplifier to convert that small current into a voltage with a larger amplitude, and then that can be processed later on. And that's exactly what they've done on this board over here. So this board is the sensitive analog stuff, which is separate from that main board, which does seem to have a whole bunch of power management and everything else on top of it. Although there are some precision analog stuff on this as well, which we will get to. All these different red blocks are low EMF relays. These relays most likely, which allow you to switch the gain of the TIA. And you can do this without introducing any error. If you look over here, we do have some precision resistors. We have a 10 meg, a 100 meg, and this could be potentially a teraohm, 0.1%, and there are even more precision resistors on there. On this board over here, there's a lot of different JFET op-amps that can be made using these amplifiers into a TIA, and then you simply switch the load of the TIA or the feedback resistor in there, and you can get the different transimpedance gains. This is a very common technique. The art is in the analog design. There are a whole bunch of cutouts in the PCB and traces which have no solder mask on them. Very classic analog circuit techniques used to produce low leakage, good isolation, good thermal stability, and everything else. And I bet there's some calibration circuitry in there which can be used from the mainframe to figure out the auto ranging and everything else, and to zero offset internal currents. On this board over here, there's a whole bunch of analog muxes and switches and more of those JFET op-amps. There's another resistor over here, another precision high power resistor as well, and this board-to-board connector simply transfer everything from here once it's been amplified to this board. The reason this doesn't need to be super accurate anymore or made of really fancy material is because, well, you've already done the amplification. The hard part is over here. Notice how all the resistors are on, these Teflon-like standoffs, really high away from the board. You shouldn't definitely touch any of these because you will introduce additional leakage just from oils from your hand. So a lot of beautiful analog engineering in a compact form factor. We will have our light pipe over here. And yeah, there's really not much else going on. Everything is nicely labeled. Definitely repairable if anything ever goes wrong because all these components have all their labels and everything quite visible. And yeah, quite nice. And here is a differential voltage measurement module. And we have similar challenges over here, except that in this situation, we also want to be able to switch between single-ended and differential measurements because both are supported. Again, this silk screen is really nicely labeled, and we can find the different sections. We do have the front end over here, which allows you to do the single-ended differential switching, as well as the AC-DC switching. Remember that these voltage measurements can also be done on AC, both for the AC characterization and the lock-in. And that's really important because you don't want to put the DC into the entire digitizer if you're only measuring an AC signal. That makes sense, kind of like a front end of an oscilloscope. And then at the same time, this section over here is the times 100 amp. On the other side, I'll show you there's a times 10 amp. In the corner over here, we have the final primary differential amplifier, which then provides a signal back into the mainframe for it to be digitized and post-processed and everything else. There are, again, cutouts here in the PCB for various protection and isolation. And the input protection circuitry for something like this is also super critical because everything is floating. You have to make sure it doesn't float above the ground too much, as well as protecting the differential inputs. And we'll flip the board on the other side so we can see it. There's a temperature sensor here in the corner for various calibration and offset corrections and everything else. The power supply section over here, some power amplifier sections there in the back again to drive the mainframe in the back, and a whole bunch of section here for filtering. This is also important because this thing can measure AC signal. It also has various hardware filters built into it that you can switch in and out. There are tons of switches on this. A lot of them are solid state. Some of them are like this Pickering relay over here is electromechanical to switch in the times 100. Again, very critical for repeatability and low EMF. All that has to be carefully taken care of. A lot of different test points. I really like the fact that it's so repairable with everything labeled, and it's so compact. There's a lot of stuff that they need to put onto these individual modules. The light pipes are visible here as well. So let's flip it on the other side because the input circuitry and input protection is also interesting. And on the other side of the board, right down the middle, you can see the input protection. There is a bit of an axis of symmetry in here because we do have two BNC inputs, of course, up to isolator with a cutout down in the middle. Lots of attention paid there. Here's the back of the times 100 amp. Actually, it looks like the times 10 amp was on the other side. I must have just missed it. And here's the unity amplifier. So by selecting between times 1, times 10, times 100, single-ended differential, AC, DC, and filtering, you get all the functionality required. Of course, the digitization and everything else is off of this board. But it's very important for the signal integrity for this thing to be maintained throughout the entire ranges. So there's a lot of communication going back and forth, and I'm sure that there's calibrations built in and corrections that needs to be done in order for this thing to work reliably across all the settings. And here's the teardown of the voltage source module, which has a single-ended output. Now, in this case, you would want to be able to drive a variety of output impedances, both at DC and AC. And as a result, they've equipped this with a pair of linear technology amplifiers. These are plus or minus 150 milliamp capable, up to 10 megahertz or so. And then they also have built-in over voltage, over current, and over temperature protection. So they really have to be careful about what they do at the output drive there. At the same time, down the middle, there is a temperature sensor. They're monitoring that temperature in that entire region. You can see that the heat sinks are soldered to the PCB. This is a situation where the heat is first laterally taken over the PCB, then up through these heat sinks. People do this when they are not able to put the heat sink on the opposite side of the board where the actual heat is coming out. And that's because of the way this whole module is put together. There's no room underneath the PCB anymore. On the side over here, we see some additional protection here for the output connector. There is a MOSFET here that's in series, I believe, with the output, so you can completely disconnect the output as well, perhaps both during operation as well as if something's going wrong. The power supply section, again, once over there, and tons of I/O expanders and serial I/O management on there because the interface is all the same, and they're pumping a whole bunch of serial configuration bits in there, and everything has to be controlled from there. Lots of muxes and other things as well. So remember that this is quite difficult because you're trying to build both a DC instrument and an AC instrument at the same time. So we will be able to measure this. These output amplifiers are supposed to be 0.2, 0.3% total harmonic distortion, so we should be able to measure the linearity of that as well, but it's going to be really useful in lock-in amplification. And here's a teardown of the balanced current source module. Now, this is arguably one of the more complicated modules because not only do you have to establish really precision current references in a balanced way coming from the triax connectors in the front, but you also have to have internal circuitry to establish the common mode voltage between them, because your DUT may expect a certain voltage across these current sources because they also have very, very high output impedance. So that needs to have a circuit with feedback around it, which is a challenge again because you have AC and DC operation. You also have this connector over here, which is a BNC to apply an external common mode voltage if you want. And then that way you can close the loop from outside of the module rather than allowing the module to set its own common mode, which you can adjust through the software as well, which is very nice. That flexibility is going to be very helpful. And then we do have a whole bunch of electromechanical relays again here to do the switch ranging. We have, microamp range all the way to 100 milliamp range. So that switching will handle that. We have the same high current drive capability amplifiers again here, which kind of makes sense again because this is a current reference source after all. And then we also have a whole bunch of precision resistors here. And these precision resistors will be the reference in order to measure against the current you're trying to set. And that's why there are multiple of them, because depending on the current you're generating, you would want to establish a certain IR drop across them. And that's all handled with closed loop systems. We do have a connector over here, which is most likely used in the SMU module. Even though I don't have one here, I wish I would have to take it apart because that would be even more complicated than all of these given the 4-quadrant voltage current mode operation. And on the other side, there's some cool circuits. I definitely want to show you that as well. These triax connectors will give you this nice low leakage path for the current, because if any current escapes because of the connector or because of lack of shielding, that will be lost and then you will get the wrong current. You're going to measure those currents for sure. Lots of analog circuitry again and switches and everything around it. It's just so compact and everything is really close together. Once you set the size of these modules, you have to fit everything in there. That's why I really want to see the SMU module. You can also see a lot of these circuitries is common, so they're clearly repeating that over and over again. Now, one other thing is notice these are all fairly new products and not a single bodge wire in all of these things that we have taken apart. That's impressive that they have gone through making sure that every one of these is perfect over various iterations they've had to do. And here in the back, we can see some of the additional care that needs to be taken to provide this isolation for these current sources. We see a whole bunch of guard islands, which don't even have the solder mask on them. Remember, every time you generate a current, you have to have almost zero potential across the terminals where you don't want the electrons to escape, because any electric field means electrons will jump across even insulating material, and those electrons would subtract from your current, and that's of course leakage. And here, by doing these appropriate guards around the critical pins, you avoid that, and you can see those guards are right around all of the precision resistors where the current is supposed to pass through. So again, lots of care has to be done. Of course, you should never touch any of these boards. They have to be washed before putting back, and I'm going to be quite careful with them. But yeah, lots of beautiful analog work again. And here is what's inside of the mainframe system. And I really like how they've made it modular and divided the system in places where it makes sense. If you look at the bottom over here, we have an Android PC. And here is where the operating system is going to run, and their software is going to run directly on top of that. It's very convenient to do this because an Android is a very well-established platform, and you can write really sophisticated code fairly easily on top of this. So this PC is almost entirely independent, and the USB port and USB-C and everything in the back is just directly accessible from this side, and it goes to the right side into the display. You can see the ribbon of the display here in the front. Underneath this big metal plate here is a big tridolar transformer and the entire power supply section. Nothing really exciting, just a lot of DC-DC converters and power management and so on. And the fan over here keeps that section cold. And if you look also carefully, you see 3 ribbons coming out here, very fine ones. Each of them are connected to a pair of those source measure connectors we saw in the back. So this is a 6-channel version, so you can see there's 3 of those, 3 times 2. And each of them have a dedicated card. So what they're doing is that they can just populate and unpopulate these cards depending on how many of those options you have. And we're going to take one of these and take a close look at that one as well. Now, if you look also in the top corner, you can see nice attention to detail. That's our Zener reference there, and they have soldered a plate right in front of it. This metal plate over here prevents any airflow over that, maintaining a nice steady temperature even though there's a fan inside of this. So they've put it right there in the corner and shielded it from any airflow. Clearly really thinking about making sure that all of these things are properly thermally managed. And all of these boards are also separate from each other. They're not even sharing the same PCB except for the connector. That gives them some nice isolation as well. Mounting them vertical makes everything super compact. filtering with the AC line coming in. There's a board down there for the GPIB, and that's it. That the rest of it is essentially software. So here's a close look at one of these data acquisition boards. Now on this side of the board, we have two ADCs. Each of these are 20-bit successive approximation ADCs, and they seem to be paired with some really high precision op amps. And next to those op amps in these two tiny components, those are quad match resistors. Internally, they can actually be as well matched as 0.01%. So they're clearly doing some kind of trimming and some kind of adjustment, potentially calibration, and these op amps themselves support E-trim internally as well. So there must be a lot happening in there to get these nice differential measurements and get rid of all the DC offsets. Measuring AC and DC simultaneously or being able to switch back and forth between them means the calibration space is quite larger. The rest of this stuff is a whole bunch of other op amps and signal conditioning. Various things are labeled here. You can see ADC inputs and outputs. Yeah, pretty nice and very compact again. And on this side of the board, we have yet another ADC. This is now a 24-bit Delta Sigma. This is probably the main digitizer, while the other ADCs perhaps are used for some other feedback and some of the other functions that are required to stabilize common mode voltages and so on. We do have a DAC over here. This is an 18-bit DAC. And I think that this is the one that's responsible for generating all the various waveforms. In sinusoid mode, we have a 3 dB bandwidth of 100 kilohertz. In triangular, it goes down to 5 kilohertz. And that's probably why, because of this DAC. Although they could be doing some other clever things in there, which would require some further kind of reverse engineering. But for now, the architecture is fairly straightforward. Now, putting the DAC and the ADCs on both sides against save space here, there's a lot of routing and isolation you need to do to make sure this all works together. So let's do some really basic measurements to familiarize ourselves with the remote heads as well as the mainframe and the GUI that runs on it. So I have the generators connected to a pair of Agilent 3458As, which are 8.5-digit multimeters, so we can measure voltage and current directly on them. And then for the receivers or the measurement units, I have them connected to a pair of HP 3245As, which are universal sources. One of them is going to generate voltage, and the other one is going to generate current. That way we can make a whole bunch of little measurements, both in AC and DC, and see how it all works out. I also went ahead and color-coded the connectors, and it's now a lot easier to know which one is connected to where. And let's take a look at the GUI and see what it is like to use this instrument. So when you power it on, depending on how many modules you have selected here, in the home screen you will see the individual source and measure modules listed over here. So in our case, S1 is the first source module, which is a VS10, the voltage source module. And you can see the number here entered at 0, and the output enable disable button is right over there. Now, if you scroll down a little bit, you can see that we can indeed select between DC, sine wave, triangular, and square wave with a certain set of capabilities that we will see on the datasheet. Now going down over here, we can do an auto range, and under the advanced setting, we have a few more things we can do. For example, the current protection is listed, which is super handy. The extreme end limits of the voltage can be set here so that you don't accidentally enter something that can damage a device under test. And the dark mode here simply turns off the LED. In some situations, that stray light coming from the front end LED can actually interfere with some really sensitive optical measurements. So it's nice that you can turn that off as well. And that's it. That's really all you can do with the source. And then here's the module information. You can name your module and write your notes and everything else. And you can always save this configuration. Now under source 2 over here, we now have our current source. So we have the ability of entering down to very, very fine digits in picoampere. Again, we have the shape can be selected here. So you can do exactly the same capabilities on providing a balanced current as you can do with the voltage, which is nice. We have the range again over here. And here under the advanced setting, we have a few more features which have to do with that common mode internal feedback to keep the voltages level between the two of them. And here we have the guard that is enabled by default, again dark mode. And you can disable an overload, which is also very handy in case something goes wrong. Here's the maximum current, 100 milliamp is respectable for an instrument like this. And there's the common mode feedback here. So the internally common mode feedback right now is enabled. So that servo is internally activated. But if you need some voltage that goes beyond the capability of what the instrument itself can do, you can actually change that to an external one and apply your own common mode voltage, which we may try during our experimentation. And then again, the module information, simple as that. So pretty straightforward in terms of the source modules. And from the measurement modules, you'll get everything that you would expect. We're reading some live numbers over here. It's connected to an instrument that's turned off, so it's basically gibberish. And the mode here can certainly be selected between DC, AC, and that really cool lock-in feature, which we will take a look at in detail. All those three measurements can be made. And then at the bottom, we have the range. And by the way, if you tap on any of these, it will give you a complete description of what that is. So it built-in help, really nice tables and really nice description of exactly what's going on. Very helpful if you're not sure about some of these settings. We do have averaging, of course, in the number of power line cycles, and it also gives you a nice description of what the consequence of that is and how it is calculated. There is also the input configuration. So here we have A minus B. So we're making a differential measurement between A and B. You can also have only measurement at A, basically ignoring port B, and then ground, which is nice for some internal testing and reference zeroing. Now, if you go under advanced setting, we have the coupling that can be selected. So if we select, for example, an AC coupling, it will bring in an AC blocking capacitor in the front, and that is helpful. And I believe it tells you the bandwidth of that. Yeah, there you go, 0.16 hertz. So yeah, that's pretty good. It gives you really close to DC. And the dark mode the same as before. And then we have an analog filter input. We saw that during the teardown. You can engage that and set the filter, and I think there's a couple of settings that you can have. Here you can choose the lowest noise or the highest dynamic range. Very typical for these kind of filters where you can add op-amp based filters to it. The actual rate in which it drops and so on can all be selected. We'll play with some of that. And then the resistance source here is listed as 2. Now, if you ask what that is, it's basically telling you that you can select the source 2 over here, and I can calculate an equivalent resistance for you instead. So if you go over here, and you can select that, you can see that it is saying S2 is not enabled. The reason it says overload is because I have high dynamic range selected here for the lowest noise. We can turn that off here and go back, and it should be good. So S2 is not turned on, but if I turn on S2, it will then calculate based on Ohm's law the equivalent resistance the system is seeing. So it's aware of what is happening on the other modules, which it has to be. That's the only way you can also do lock-in amplification and lock-in measurements. So we'll get to some of that experiments as well. Pretty straightforward and easy to use, and you click that, that goes to just a voltage measurement. Now under M1, which is the other measurement module, here we have our current measurement, which is single-ended. I wish this was also differential, and also if it had a coaxial, a triax connector at the front end, it would have been also nice. So here again, we can do similar things. You can see DC, AC, and lock-in can be measured. Very similar range, and LPC can be selected as well. Under advanced setting, you can set your input bias. Because you're measuring current, you can set what voltage to impose on it. Very helpful depending on where that current is coming from, and we will play with that as well. Again, we have the filter, and the resistance mode can then set this time be to the opposite, which is S1. So between the two IV, you can get the Ohm's law. So really nice and very, very simple way to navigate the GUI. Nothing unusual there. And we have a button over here, which then puts them on a bit of a grid. You can see you can see all of them at the same time, and then you can go into the advanced features and remove them and edit them. That's also good. And then if you have more modules, they fit there with just smaller icons. If you swipe here on the left, you get some more settings in just internal configuration of the instrument, and here you also have your GPI book configuration as well, so you can set your ports and so on. Very nice. So yeah, very simple. I'm sure this is a platform that's going to continue to be built and be made more and more sophisticated, but now we kind of understand how to manipulate these modules. Let's do some measurements. Before I forget, there are a lot of things that can be added to the GUI, which I recommend that they do, that will improve the usability of this mainframe significantly. For example, there's no plotting function or a simple table generation of the data that is saved, minimum, maximum, statistical, and distribution data that can be viewed directly on the screen. These simple additions will enable the user to be able to quickly get ideas about sophisticated sets of data and compare them between the different modules, and even do manipulation between two modules. So for example, if I have two current sources and two voltage sources or measurement units, I should be able to interact between them and do some computation. There's no math function or hold function and things like that. So it's clearly very early in its development, but I can see that it is headed in the right way because the platform and the foundation is really laid out. It's just a matter of writing a whole bunch of code on top of it. Let's do a very quick voltage measurement using the VS10 module directly connected to our multimeter. Right now the output is disabled and somewhat floating. That's why we're seeing minus 45 millivolt. I'm going to enable the output with 0 volt. That should give us a good reference baseline 0 volt output, which is pretty important. Let's see what we get. There you go, 0.005 millivolts, so pretty small there. So let's go ahead and give it 5 volts. It should have no problem generating 5 volt for us. Here's 5 volt. Let's see what happens. There you go. There it is, lots of 9s, so no issue. Now this is a plus and minus source, so we should be able to flip the polarity pretty easily. So here's minus 5 volts. There you go, minus 5 volts, again with lots of 9s in front of it. This does go up to plus and minus 10, so here's the extreme edge at minus 10 volt. And yeah, you can see it's exactly the same offset actually. And here is 10 plus volt, extreme end on the other side. And it is going to be the same. So this does have ranges down all the way to 10 millivolt. So when we generate 10 millivolt, it will be full scale at its lowest range. And there is 10 millivolt there. Let's see. There you go. So that offset seems to be a slope because it's carrying through. So for example, if I go from 10 millivolt here to 1 millivolt, I bet I will see that 0.8 again. Yeah, there it is. You can see that this number gets just really simply pushed out. So it's some constant offset. Now, some of that might also be from the meter I haven't calibrated or ran the ACAL on the 8.5 digit meter for some time. and we should be able to flip the phase on this, and it has to be quite symmetric around this point. Let's see. Stabilize. Yeah, so there's a little bit offset there. If you look at that, the mean has moved a little bit between there. So it looks pretty good, but this also should be able to do AC voltage. So let's try an AC measurement. So I have the instrument set to 1 volt RMS. You can directly enter that value in RMS, and the frequency is at 500 hertz. Let's go ahead and enable that, and we should be able to measure a nice 1 volt RMS. There it is. Of course, the multimeter is a true RMS meter, and it's really close to 1 volt. Now, one of the nice things you can do is you can also enter a DC voltage as an offset, which is really helpful if your DUT requires a DC, but you want to apply an AC on top of it, for example, for lock-in purposes. So right now I have a DC of 2.5 volt on top of this, and if I go to DC here, you can see that we will measure our 2.5 volt offset. There's a little bit more error here in this situation, and it jumps a little bit around, but nonetheless, it is able certainly to do that. And you can also set the range on each of the AC and DC separately. So if you have a really, really small offset or a really, really small AC signal, you don't have to use the same range on both. So they've thought about, minimizing the errors in those. And I can, of course, completely turn off the AC as well, or the DC rather. So here we go. If I just turn it off, the DC will go down to 0. There it is. If I go back to the AC, the AC is still there at 1 volt. So that is pretty helpful. You can see there's a little bit of offset when the two are active at the same time because there's a lot going on, but the combination of these two will be very helpful. And for the BCS10 module, we should be able to do some balanced current measurement as well. So I have it directly connected to the instrument, and it is enabled and set to 0 amps. And you can see we're reading almost 0. So let's go ahead and set this to 1 milliamp. Here is 1 milliamp, and let's see what we get. It should be almost exactly 1 milliamp, and there it is. Pretty good. We can, again, reverse the polarity as well, and it should do exactly the same thing in the opposite direction. So it works really well. Look at all those zeros. I mean, it is doing a fantastic job. Now, the range of this goes all the way down to 1 microamp. So I can go 1 microamp. That will be full scale at the lowest range that it does have. There you go. It should be pretty close. That is very, very close. There you go, 1 microamp. And we can make that even smaller. We can do, let's say, 0.01 microamp. Now that we're dealing with now extremely small amounts of current. There it is. 10 nanoamp, almost perfect. Now it does go down even lower than this, but at some point you're going to run into the wall where you need to use a proper picoamp meter to really measure it. When I can enter 1 nanoamp as well. There you go, 1 nanoamp. You should have no issue with 1 nanoamp. There it is, almost exactly 1 nanoamp. It's pretty impressive. Again, the triax connectors here really help because it does give you that ability to really isolate things. And even here, we should be able to perfectly flip the phase and get an inverse. I should say flip the polarity. There you go, and there is -1. And we can connect it to a picoamp meter and measure below that, but it certainly is going to work. And it does have all the same abilities as the voltage source. For example, it can do AC as well. And for the sake of completion, here is a 1 milliamp RMS AC current being pushed into the instrument, while simultaneously there's a 10 milliamp DC current. So if I go over here and look at the DC, you can see that there's our 10 milliamp DC current. So you can do a small AC on top of a large DC or a small DC on top of a large AC. It doesn't matter. Both of those are supported on separate ranges. And on the measurement, the VM10 is a differential voltage measurement. I have shorted one of its inputs. Therefore, I should be able to measure, for example, up down here, A minus B or A should give me essentially the same result. So right now we're making a differential measurement with respect to 0 on the other side. Let's apply 1 volt here. There's 1 volt, and there it is, 1 volt. One thing that's a little bit odd is that I'm not sure why it is auto-ranging itself to 10 volt, because it should be able to very easily auto-range itself to 1 volt, and that should give me the exact same result, and it does. So perhaps the auto-ranging is being a little bit conservative there. Now, if I go over here and I change this from A minus B to just A, I should get essentially the same result, and I do. There's going to be some potential EMF generated at the connector short, but in this case, it's completely removed, measuring it directly from the internal reference there. Now, I should very similarly be able to apply, let's say, -1 volt. Again, this is completely symmetric. There it is, -1. So there's a tiny offset in there. That's most likely coming from the 3245A that I'm using, but it's unclear which one is has the slight offset on there. So let's go back to, let's say, measuring something a little bit larger. I should be able to do 10 volt here without issue. And there it is now. It is, of course, on the 10 volt range. Makes no mistakes. I think some basic nulling function should definitely be added here. So if I go over this area here and make a ground, I will read the internal offset of it, -20 microvolt, which is actually about the offsets we were seeing. So if there was a nulling function, you could null this out and it would subtract it, or perhaps an automatic nulling function that it could run every once in a while. These are basic software stuff that I really do hope that they add to this. And here now I'm measuring an AC signal, 1 volt peak to peak, which is about 353 millivolt RMS, and is doing that correctly. It's also giving us a DC measurement at the same time, so it's able to do both of those because it's just digitizing it. Now, it would be nice if it also gave us the frequency, but it doesn't directly measure that. Again, easy thing to add, and the frequency here is 1 kilohertz. Now, if I go over here and change the coupling from DC to AC, it's going to put the AC blocking capacitor in the front now. It should be smart enough to remove that because this is meaningless right now, so that would be nice if they get rid of that when you're in that mode so you can easily tell which mode you're in. And now we can add a filter. So if I go over here, it's on the highest reserve, and let's say we add a low pass filter. Now the frequency coming in is 1 kilohertz, so I can add a 100 hertz filter. And that's going to, on a 6 dB per octave, give us the attenuation we need. And check this out. Yep, it works. It is indeed doing that attenuation for us at that frequency from the decade away. So all of that looks really nice. Now obviously we also have the locking capability, as I mentioned. So one more thing, let's do the current measurement too, just for completion, and then we'll get to some more complex experiments. And here, using the single-ended CM10 current measurement module, I'm injecting 1 milliamp DC into it, which it has no problem measuring. One other feature this module has is that it allows you to enforce a specific voltage across this terminal. And that can be really helpful depending on the sensor or whatever it is that you've connected to it if you need to maintain a certain voltage across it. So right now it's set to 0 volt, and if I enable that, if I go back up here, you can see that the current changes ever so slightly. I'm not sure why. It does that only at this range, and I'm verified it's not coming from my source. It's really doing it on its own. But if I go down here and change this to, let's say, from 0 volt to 1 volt and enforce 1 volt across the terminal, go up here, you can see that it fixes that without any issues. Now, my source cannot generate an AC current, but it can, of course, measure that as well. We can also try a much, much smaller value. Here we go. There's 100 microamp, no issues at all. And we can go even smaller than that, and you should have no issues that it is 1 microamp, and it's pretty accurate. Now, if you want to go well below that, we're going to need, again, a much better source to generate this, and I wish it had a triax because it would be helpful in some situations with the guard. But yeah, the current measurement also works nicely. And just to show you that it indeed is only on this range, if I go over here and put that back to 0 volt there, and press enter and come back up here, you can see that it doesn't change that. So somehow only around that value we see that slight shift in current. So now let's do something a little bit more complicated. What I have here on this breadboard is a bipolar transistor, an NPN type device. And I want to characterize its beta, its current gain, but I also want to know how beta changes as a function of temperature. So I'm using all of our modules to do this. First, I'm using the balanced current source to inject some current directly into the base of the transistor. That current going to the base is going to turn on that device. And I'm using the balanced voltage measurement to actually measure the base emitter junction voltage, which is essentially a diode. So the current source and the voltage source are going to characterize the base input. Now at the same time, I'm using the measurement current source here at the bottom, and I'm measuring the current between the collector and the emitter. That's going to tell us the ratio between the base current and the collector current. And then using the voltage source, I'm going to show you a zoom view of this in a second. I have a resistor that I've thermally glued to the top of that bipolar. By putting a voltage on that resistor, it's going to burn some current and it's going to dissipate some heat. And that heat is going to get coupled into the bipolar, raising the junction temperature. And then we can live measure the effect of that on the beta, on the current gain. So all of these devices are now used at the same time in order to do this characterization. Should be pretty interesting. And on the close-up, you can see our bipolar transistor over there. We have emitter, base, and collector as the 3 terminals. And on the top of this, we see the resistor that is thermally glued to the top. And that's going to change the junction temperature as I put power through the resistor. Now remember that because we're injecting current into the base, we can actually use the base emitter voltage to estimate the temperature too. That's the beauty of this setup, because instead of using a voltage with a resistor to drive the base, we're directly driving with the current. So we're keeping that parameter constant, and therefore the base emitter junction can now be independently measured. So let's see what we get. Now let's also take this opportunity to take a look at the MeasureLINK software, which is a platform Lakeshore uses to communicate with a range of their instruments, including the M81. It can do really advanced sequencing and scripting, and it has a really good, well-documented API, so you can write all kind of different codes, including in Python, as well as the one that runs inside of this platform. Now it is a licensed subscription-style model, so you have to evaluate whether it fits your needs. But if you're doing a lot of automation and want to develop a complex sequences, then it can certainly be worthwhile. Now in order to set it up, it's pretty straightforward. You go into the system configuration, you add your instrument, and here you can define and name them and exactly define how they're connected to the M81. I've already done that. Now once you do this, you get this little system status window here on the right side that you can always keep on top so you see what's going on. If you enable it, it will do a live continuous reading directly from the M81 on everything that's set up. Now one really low-hanging fruit that this does not have is that you cannot change these parameters on this menu, and this absolutely should be included. You can enable and disable the outputs, and that's about it. But having this ability to interact with these numbers on this is vital, because it makes the software so much more usable, especially if you want to bring people in and for them to have jump in here and evaluate it and use it and subscribe to it. This should absolutely be included. Now, if you want to change some of these settings, you'll have to go over here and you can say what setting has changed. So for example, if I want to change the amplitude, if I select the amplitude over here, I change it, let's say, from 10 over here, and I change it to 20 and press enter. If I say apply configuration, then it writes it in, and you have to go back here and enable it again. And then once you do that, you can see that number has now changed to 20. But if you could do it directly on this, it would be a huge advantage. Definitely should be included. Now, having said that, let's see how our transistor is going to behave. I have the base current set to 10 microamp, but it's not enabled, and therefore we expect the transistor to be off. And if you look at the base emitter measurement voltage, it is indeed well below the forward bias voltage of this transistor, which should be around 0.6, 0.7 volts. And as a result, there is no current going from the collector to the emitter. That also makes sense. The voltage here at the bottom, 10 volts across the resistor that sits on top of the transistor, is also turned off, so there's no heating effect. Nothing's going on. Everything makes perfect sense. So let's go and enable the current. Now, as soon as I enable the current, look what happens. We develop a forward bias voltage across the base emitter junction, and we're drawing about 2.1 milliamp directly from the collector to the emitter. And that is exactly what you would expect to happen. The transistor is now turned on. Now, keep in mind that I have turned off the common mode feedback for the current source, because we have a shared port emitter between these two measurements. This all is really nice, and from this we can quickly calculate the beta. Right? We have 2.2 milliamp or so because of 10 microamp of base current. The beta is about 220, which is exactly what it should be for this transistor. So this is really nice, all makes sense. Now, as soon as I turn on this 10 volt source, the transistor begins to heat up, and we should observe a change in the base emitter voltage, and we should also observe a change in the actual beta. Let's see if that's correct. Here we go. Turn it on, 10 volts over there, and look at this. Look what happens. The base emitter voltage is constantly dropping. That is consistent because we have a minus 2 millivolt per degree Celsius change in the base emitter junction as a function of temperature. It's going in the opposite direction. But at the same time, you see the beta is getting better and better. This is in fact a fundamental property of a bipolar transistor. This is essentially a thermal runaway effect that can happen with bipolar transistors. Because their VBE drops, their beta actually grows because of the semiconductor material properties, and you get more current gain from the transistor when it gets hotter. Now, this is obviously up to a certain point. Eventually, it goes the other way when it gets way too hot. But this is a really nice and quick demonstration of this thermal runaway problem from these kind of bipolar transistors. And you can see how much the base emitter junction has dropped. From this measurement, you can actually estimate the temperature change of the junction too, so you can characterize it completely. If I turn it back off again, you see that it will start going back to ambient temperature. It's going to begin to rise, and everything goes back to where it used to be. Pretty amazing. Now, I'm sure you have noticed by now that in order to keep the transistor in the correct operating region, you need to define the proper collector emitter voltage across the transistor, otherwise it will not be in the active operating region. And in fact, that's one of the really nice features of the current measurement module here, because you can define the bias voltage across its terminals. And in this case, I have defined it at -5, which becomes 5 volt from the collector to the emitter when it's connected to the device. And that keeps the transistor in a really nice operating region. In fact, by playing with this voltage, you can find out where the transistor enters saturation. When the collector emitter voltage becomes too small, and then you will forward bias the base collector junction, you will bring the device out of the region typically used for amplification. So that's another super important and critical capability of this, being able to define the voltage across the terminal. Now, Lakeshore's primary capabilities involve sequencing and scripting, allowing you to interact with the different instruments as well as collect data from them in some kind of an automated fashion. So you can do things like measurements, collect data from the different M81 modules that are connected, various loops for repeated measurements, and you can see that there are some other capabilities in here like field control and so on, which are not relevant to the M81, but relevant to some of the other instruments that Lakeshore makes, as well as controls, so you can interact and change the settings of the instrument, as well as collecting data and plotting them. So here I have made a really simple measurement, so we can do some essentially IV curve of our transistor. This is going to consist of a nested loop. On the outside loop, I'm controlling our current source, pushing current into the base of the transistor, and I'm sweeping that from 10 microamp to 70 microamp in 7 steps. So essentially 7 different biasing conditions of the base and the collector current. On the inner loop, I'm controlling the collector emitter voltage by directly changing the DC voltage that appears on the current measurement unit. So you can see that it goes really fairly deep, allowing you to control some of the subtle parameters of this. And that's going to sweep from -2 to 0, which is going to appear as from 2 to 0. So basically, we should be able to see the transistor from the active region and being completely saturated when the voltage across the collector emitter becomes too small. And then plotting all the data. In the plotting, you can choose where to get the data from depending on what measurement you have actually created, and you can have multiple different measurements. This thing can get pretty complicated. And then I've named the axis so it can do the plotting. And once I'm done that, you can see that it is alive right over here. Let's go press play. And it's going to go through the different measurements. So if you look over here, you can see that it's changing the bias voltage slowly, making it smaller and smaller. And for the values that are large, this current isn't changing at all. But once this gets pretty small, you can see that it's beginning to get into the saturation and the current's going to drop. And once it finishes that, it jumps into the 20 microamp. So it's just going to simply go through step by step and eventually finish this whole two-dimensional sweep. So we should be able to take a look at the curve. And the measurement is done. And here's a table of all the numbers that it has corrected. You can see if I go all the way to the top, starts from a 10 microamp and is varying VCE, and it goes through it all the way to the end, which is 70 microamp. And if I go to the plot, check it out. It's backwards, of course, because the numbers are starting from negative, but this is a very classic IV characteristic of a bipolar transistor. Now, I couldn't figure out how to get rid of these lines going across because this nested loop, for whatever reason, connects these two endpoints together, but I'm sure there must be a way. If you also look closely, you can see that the slope here is very, very flat, and you're beginning to see a little bit of slope as the transistor is biased more and more aggressively. And that's also expected because the output conductance of the transistor continues to get worse. It's increasing. The output resistance keeps dropping. As you bias it more aggressively, the early voltage is changing. So yeah, you can see how easy it is to very quickly set up something and do multi-dimensional sweeps directly on here. Now, what it's really doing in the background is that it's running a script. And the nice thing is, once you set up your sequence here graphically using the GUI, you can export it into the script, and then you can modify it in any way you want. I've already done that, and here's the equivalent script of what we just ran. This is automatically generated by the software. Now, this is super helpful because it gives you a quick head start to get your setup the way you want and then modify it to your heart's content, write whatever you want, expand it, and the API is completely available. So this becomes very powerful, especially if you want to make really sophisticated and very unusual types of things you don't want to create it with the GUI. So this combination of a sequencing and scripting, I like that. I think that can go a long way. So the next thing I want to take a look at is the quality of the signal generated by the sources, both the voltage and the current source. And the reason is because when we want to use the system in a lock-in configuration, sometimes you may want to look at the second harmonic of the signal. And in that situation, the second harmonic has to be really clean from the source, otherwise you won't be able to tell where that's generated. Is it from the source, is it from the device under test? So I'm going to use this Quantasylum as a measurement over here. We've already reviewed this in a different video, and it has a massive dynamic range and very, very good internal THD. So we should be able to easily measure the quality of these sources. The first case is super simple because we have a single-ended output coming from the source voltage going into one of the channels. Let's take a look. So let's see what we have here. Right now the source's output is disabled and we're seeing a certain amount of noise depending on the impedance it presents at the output and the measurement instrument. Now this is not the actual power spectral noise density because depending on the range of the output when the output is enabled, this value will change. We do see, however, a little bit of a low pass filtering here, which is normal and good because the instrument cannot generate frequencies up here, so there is an inherent low pass filtering at the output drivers. All that makes sense, but I am interested in seeing what kind of quality signals I can generate at various output powers. So I have the instrument set to 1 volt RMS and 1 kilohertz. Let's go ahead and change this to 12 dB volt here so that we can measure this well. And let's enable the output and let's see what we get. There it is. Look at that, 999.971 hertz. So it's falling within one of the bins close by. These are not coherent locked together. And we're using a flat top windowing. We have some skirt in here, but it doesn't matter. Primary energy is here. And look at the THD, minus 81 or so dB, which is pretty good. It means that you can rely on a certain amount of harmonic if you need to measure lock-in at the second harmonic of the signal. This is a fairly clean source, nevertheless. Now we can go ahead and increase that, let's say from 1 volt to 2 volt RMS. Let's see what we get there. There it is. It's 2 volt RMS. And it actually got better. It's about minus 85.5 dB now for a THD. Fairly clean signal. You can see the harmonics over here. At the higher frequency, a little bit few additional tones in there, but it really doesn't matter depending on what you're using it for. But I'm pretty happy with the quality of this. Now we can go the other way and make the signal quite a bit smaller. Let's say 0.1 volt RMS and see what we get. There you go, goes down. We can change this to 6 now. You can see how the noise also changes because the range of the signal, of course, changed. And that means that the noise went down with it, which is a good sign, which means the SNR is maintained. And minus 80 again. So we're around that kind of minus 80, minus 85 dB value fairly consistently. Now, if I go really small, let's say 1 millivolt over here, That's where we see really how low the noise can get. If this system was completely noiseless, this value could go down to minus 150 dB volt, but that's very, very good. And you see the tone sticking out over here. This THD doesn't mean anything anymore because the harmonic is not visible through the noise, and now we're just seeing the primary tone. So pretty impressive what this can do. We can also change the frequency. So let's go back to the original value we had. Let's say we go back to 1 volt RMS over here. We can change the frequency to, let's say, 250 hertz. Going at the lower side, see what kind of THD we get here. There it is, THD minus 84. Maintains that reasonably well. Let's double it to 2 kilohertz from the original value. And at 2 kilohertz, what do we get? We get about minus 79, again, around minus 80. So it's pretty consistent. I've tried it across different places, and I get a good value. And the fact that the power spectral noise density changes at different ranges, because it has many, many ranges as we saw, is fairly good as well, because it maintains that nice SNR. Looks pretty good. And similarly, we can do exactly the same kind of measurement, except now we can do it in a balanced fashion from the current source generator. Now, because it needs an impedance to generate a voltage so we can measure it using this, I have a load directly in the middle. So the current is pushed through a load, and the voltage across the load is measured differentially using the quant asylum over here. We can then capture the THD in exactly the same way. So I've gone up and set the resistor to be 1 kilo ohm, and therefore if I pass 1 milliamp RMS current through it, I should see 1 volt RMS. And that's what I have set the instrument for. Let's give it a try. Here's enabled, and check it out. We see about 1 volt RMS, and look at the THD. It's about minus 80 again. So they've kind of matched that to make sure that they're about the same in all cases, which is nice. Now I can go ahead and change the current, and it stays roughly the same. But another degree of freedom we have here is to change the resistance, and that matters a lot here, because as I increase the resistor, the voltage swing appearing across the balanced terminals of the current source will change and will grow, and eventually will push into the nonlinearities of the output drivers there, especially if the common mode feedback is turned on, stabilizing the voltage, and that's a pretty tough test. So let's go ahead and increase the resistance and see what happens. There you go. You can turn this potentiometer here. You can see we're already at 3 volts. THD doesn't seem to be affected by much. Increase it a little bit more. We're beginning to lose a little bit of THD, but this is 5 volt RMS already. Let's increase it. Let's go just really aggressive. I mean, let's push this thing. Let's do a 10 volt RMS, which is a fairly large signal swing. Look at that. We lost about 9 dB of THD, which is not bad. Again, 10 volt RMS is a lot of swing, a lot of peak-to-peak voltage appearing there. And these circuits are maintaining a very good linearity, as well as maintaining that common mode feedback servo built into them. Also note, because this is a differential drive, we're fundamentally limited really only by the third harmonic, that the even mode harmonics are pretty good. So nice balanced output driver. Everything looks good. It's an impressive result. So for our next experiment, let's try and measure an RC circuit and add some complications to it as we go forward. So we're going to use our voltage source over here to excite a resistor series combination. The resistor comes from this resistor box, which I can dial into essentially any value that I want. And the capacitor is a 10 nanofarad capacitor that's directly on the breadboard. I'm also simultaneously monitoring the voltage across the capacitor using the differential voltage measurement module. And that's going to allow us to use this combination as a lock-in, incident wave going in, coherent measurement coming back. I'm also measuring voltages and other parameters across the components. I'll show you a zoom view version here in a second. I also have a diode over here, which is not currently on the breadboard, but I'm going to add that in parallel with the capacitor later, and that's going to create havoc on this measurement. And we can see how we can avoid that and detect that there is a problem. Let's take a look. The close-up, everything is pretty simple. Here's our 10 nanofarad capacitor, and the resistor is connected in series with it using the resistor box, and in the far distance is the diode that's not currently being used. Let's do some measurement. So the first thing to do is to define our incident signal for lock-in measurement. I'm going to use the voltage source here at 1 volt RMS, and the frequency is 1 kilohertz, and there is no offset on there. So let's go and enable that signal. Here's the signal there. And if I go into the measurement, I've set the voltage measurement mode to be in lock-in, and the reference source is now S1. So therefore, we're going to use the frequency and the phase of S1, which we have already defined, in order to make our lock-in measurement. I'm also showing the measurement here in polar format, which is very helpful if you're looking for a particular phase transition, which is what we're trying to do with a low-pass filter. You can also change that to be rectangular if you really want to, more traditional. But in this case, definitely looking at it in the polar helps. Now, this instrument should also be capable of showing you the DC voltage across the device, as well as doing a lock-in measurement. So in this case, there should be no DC voltage. In fact, I have verified with a multimeter that should be 0, but it's measuring 300 millivolt. And I believe this is just simply a mistake in the firmware, because this value is going to depend on how the filtering is calculated, because it's mathematical. And now I have the averaging filter here turned on. If I set the averaging filter to only 1, it's going to calculate over only one cycle at 1 kilohertz. So it's going to give you a gibberish result because depending on the sampling point and so on, you're going to get a different apparent DC offset, different average DC voltage. But once you have this at 256 or higher, it should really have no DC left over, but it still somehow shows 300 millivolt. I could not get rid of that. Now, there are several other interesting things you can do. You can turn on this low-pass filter, which is in fact an infinite impulse response filter. It's going to be really nice for making completely accurate and stable measurement over a long time, but it does take a long time to settle, so I don't need it here. It's actually turned off. There's a few other things like digital filtering and additional coupling at the input. You can even do actual hardware filtering. All of that can be added, which we looked at before, so we don't have to dwell on it too much. Now, at the very bottom over here, we have one other thing, which is the reference phase shift. Now, normally, in a system like this, if you have any phase offset, you can just press auto, and that auto completely cancels that phase offset for you, sets the reference measurement at that point to 0 for you. But in this case, if I keep pressing it, you can see it kind of jumps around. Sometimes it goes even to 11 or 12. There's this -9, -2, and it keeps changing. Now, it shouldn't be doing that, because I think this is also part of the same bug we saw earlier. Because if I go ahead and change this to just 1, and I go back, and I try the same thing, let's do it a few times, you can see that it kind of is much, much more stable. It changes a little bit, but you see it stabilizes to fairly constant value at this point. Yeah, it doesn't change anymore. That's pretty good. That's what you in fact want. You can see that this is set to 0. But as soon as I put this to 256 or higher number, we get to have that little bit of error there. So I think that's part of the same issue, and I'm sure they can fix that. You can see -14. That doesn't make any sense. So it's clear that we're just going to deal with -4. So this -4 degree, what does this mean in this case? Well, we have a 1 kilo ohm resistor in series with our capacitor there. So there's a little bit of phase shift that's to be expected. Even though that's well below the 3 dB bandwidth of our filter, that's why we're not seeing anything significant. But now we can go on, turn the resistance slowly up, and get it to be at exactly 45 degrees. So let's dial in this resistor. Right now it's at 1 kilo ohm. Let's go to 2 kilo ohm. There you go. You can see that the phase lag gets larger, exactly what it should be doing. So here's 3. Let's keep going. Here's 7 kilo ohm. We're getting closer to that 45 degree we're looking for the 3 dB bandwidth. Here's 12 kilo ohm, almost there. Here's 14 kilo ohm, and maybe one more. And here's 15 kilo ohm. And check it out, 15 kilo ohm and 10 nanofarad make exactly a low-pass filter with a bandwidth of 1 kilohertz, which is what we have here. So it's completely consistent. It all makes sense. This number also changed because, of course, this number is now a square root of 2 smaller, exactly as it should be. So it's computationally calculating this. As you can see that there should be no change in the voltages there, but there is. So that's a part of the same bug. But there you go. You can easily now measure the 3 dB bandwidth of this filter. But now let's throw a little wrench in this measurement. Let's make it complicated by adding a diode to it. And here is our little diode in parallel with the capacitor. And now with the diode in parallel with the capacitor, the measurement no longer makes sense, because even though the phase has shifted only by a little bit, the amplitude has dropped significantly. And this should be obvious why that has happened. And that's because the voltage is large enough to forward bias the diode. So we are clamping it down, and it can no longer stay at 1 volt divided by the square root of 2 at the 3 dB bandwidth. It's less than that. In fact, if I go ahead and unplug the diode there, you can see that it goes back to exactly where it was. So then you put the diode back and see if there is a way to cleverly detect this problem with the instrument itself. Well, because we have a lock-in amplifier, we are also able to do measurements on multiple harmonics of the input. Well, if the diode is being turned on and clamping, it's going to generate harmonics, nonlinearities, and those harmonics are going to put energy into multiples of the frequency at the input. We should be able to measure that. So instead of measuring the reference harmonic 1, which is at 1 kilohertz, let's measure reference 2, which would be at 2 kilohertz. Now, if I go up here, look at that. There's actually signal in the second harmonic, and there shouldn't be. And I can prove that to you again. If I remove the diode, here you go. Look, it goes down to microvolts because the nonlinearity is almost non-existent. And that's the beauty of having the source to be inherently itself very linear, because you can make these kind of measurements. So let's go ahead and put the diode back over here again. It becomes nonlinear again. So now we should ask ourselves, well, how do we solve this problem? Well, an obvious way would be to go back over to the source and change the incident signal, make the signal smaller and smaller so that we don't forward bias the diode. But that often means you are lowering your signal to noise ratio as well. But if I want to do something else, well, the nice thing about these sources is that they can also do a DC voltage as well as an AC voltage. So we can apply a DC offset and move that sinusoid below the value which it can turn on the diode. Let's give it a try. So instead of having an offset of 0 volt, why don't I enter an offset of -1 volt? Now if I do that, if I go back to the measurement, look at this. The amount of second harmonic has gone down significantly. It's still not as low as its baseline because we're probably just turning on the diode just a little bit. But if I go back over here and I change this back into the fundamental measurement, we should be able to be roughly where we were before. And look at that, we are measuring exactly the correct value. Now there should be -1 volt across the diode. And interestingly enough, it's almost measuring that correctly here, but still that lock-in still has some issues with the lock-in DC voltage. And how nice and easy it is to manipulate the setup and find problems with it simultaneously. And this is because of the strength of both the sources and the measurements and all the flexibilities they have. And for our next experiment, we're going to try and measure the level of a liquid in a container. And we're going to do this by bouncing ultrasound on the surface of the liquid and looking back at the reflection. By changing the level of the liquid, we will change the entire time it takes for the ultrasound to bounce against the surface and come back to the detector. And we're going to drive the first ultrasound transducer from our voltage source, and we're going to analyze the signal on the second one using the voltage measurement, and we're going to do all of this, of course, in a lock-in fashion so we can get a nice, clean measurement. And here's our setup over here. There are two transducers in here, and the liquid in here that's purple, that's just so they can easily see the surface of the liquid. And there's a little hose in here, which we can do to drain the liquid away, and therefore the surface of the liquid will drop slowly over time as we drain it. I'll show you a side view of this as well. Everything in this setup is going to work at 25 kilohertz. And in principle, we should be able to look at the phase shift and estimate the level of the liquid. And here in the side view, hopefully you can appreciate the situation a little bit better. So here's our transmitter, transducer, and here's the receiver. And of course, the surface of the liquid is somewhere down there. Let's give this a try. Now, before we start the flow of the liquid, we can make a baseline measurement. And you can see that we're receiving 64 millivolt or so, and the phase is stable around 164 degrees. Now, this phase is arbitrary. We're looking for the delta and the difference as the surface of the liquid goes down once we drain it. And the applied voltage is 2 volt RMS into our transducer. I made a really simple script like before. It's just going to capture the magnitude and the phase over time as the water level goes. Let's start it. And check it out. Look. The phase is slowly changing as the surface of the water begins to go down. And it's a very nice gradual decrease. Now, once it starts zero, once it gets to zero, it's going to go negative. There it is. Now, the amplitude is going to also slowly go down because of course, the distance is changing and everything is not perfectly aligned. But it's going to be interesting once this whole sequence runs. It's going to run for quite some time, and then we can take a look at the plot. And here's the waveform after some time. There are some interesting things to observe here. At the very beginning, before I let the liquid float, the phase is flat, which makes sense because the surface of the liquid isn't moving. And then as the surface begins to drop, you can see the phase begins to change. And this doesn't unwrap the phase, so it goes from -180 to +180. And then as I was looking around, I gently bumped against the table, and the liquid kind of flew a little bit around. And you can see that little ripple effect was until the surface of the water actually settled back down, which was interesting. Also, some reflections around when you kind of look around it can change the phase. But if you leave it undisturbed, you get really nice waveform results, which is exactly what you would expect from this. Now remember that the wavelength at 25 kilohertz of sound in air is about only 13 millimeters or so. So we're talking about even very small perturbation of the surface can have a big phase change. But yeah, this is a pretty interesting result and very consistent with what we would expect. And in this next experiment, I want to explore the sensitivity of glass case diodes to UV light. Now, this may seem like a really bizarre experiment, but it's actually quite relevant. There have been situations where you have bare die DC-DC converters that are directly placed on a PCB, and they are so sensitive to UV light that a flash of a camera would reset the system. I believe this has happened to some Raspberry Pis in the past. And this is, of course, a photovoltaic effect. These high energy photons from the UV will hit the PN junction, and they're going to knock off and free some electrons. Those electrons are basically current, and they can disrupt some operation of the system. So in this situation, I have a laser diode over here. We're going to hit a glass case diode with it. And because it's transparent, it's going to hit the PN junction, and we see if we're going to produce any free electrons, any charge on the other side. Now, it's not always possible to directly modulate your source. So in this case, we're applying a constant DC current to turn on this laser diode. If I were to modulate the laser diode directly, it doesn't behave very well under those conditions. And on the other side, we have our detector. Now we want to remove all the effect of ambient light in this system. We want to really isolate the effect of only the UV photons here. And we do this by using a chopper. That chopper is going to create a periodic repetition of those pulses hitting the diode. And now we need to lock into that using the lock-in amplifier function. Now the nice thing is that this chopper is actually connected to this Stanford research device. And this is going to create a reference frequency, which is exactly the repetition rate of that chopper. And they're feeding that back into our M81 system here. And that's the beauty of this, because this can also lock to an external source, and it doesn't need that source to necessarily come from one of the other modules. So you could use an external modulated device to still do complete lock-in measurement. So now we're combining a DC source with an AC measurement and an external chopper. I think that's pretty cool. Let's take a closer look at this interface. And here's a close-up of this situation. In the back, on the other side of the chopper, we have our glass case diode, and on this side, we have our UV laser. And you can see a little bit of the reflection bouncing off the surface of the chopper every time it passes in front of it. Now, if I bring a piece of uranium marble very close to that interface, you can see that we get a very classic fluorescence. There it is. You can see the beam of UV photons going through the uranium glass and creating that beautiful fluorescence effect. So I do have that laser essentially shining directly through the glass at the interface of the PN junction. Now, for the purpose of the measurement, it's important to get a baseline to make sure that what we're reading is actually real and the result of the laser diode. So I've gone ahead and turned off source 2, which was pushing 35 milliamp through the diode. So right now the UV diode is turned off. If I go under the measure 1 module, which is here in this case the current measurement, you can see that it's set to lock in and it's set to reference in, which is coming from the chopper. And it's measuring 158 hertz, which is exactly correct. Now, a nice feature of this particular reference in mode of operation is that it will detect if the reference is not stable. So if I go ahead and touch the wheel, that's going to cause its frequency to change. You can see that it says settling and unlock. So it doesn't just make erroneous measurement. You know that it's looking for a certain stability in the reference coming in, which is very, very good. Now it's measuring some stray currents in the femtoamp, picoamp range, basically almost nothing. The diode on its own, just with ambient light over here, even through the chopper, is producing absolutely no signal. So now I'm going to go ahead and turn on the laser diode. Go over here, turn on 35 milliamp right through it, enable that, and go back. And check it out. Now we're getting 4.41 nanoamp with a very, very stable phase angle. So that means that is really the charge induced because of the photovoltaic effect and because of our laser diode. Now this is on the other side of the chopper, so it's really locked to that frequency. Even if I were to shine some other UV light on that, it would make no difference because it needs to be at exactly this chopper frequency. Now if I change the chopper frequency, for example, go a little bit higher, chopper spins faster, and this is going to go up, it's going to catch up to that. You can see that it doesn't make much of a difference. To a certain point, the responsivity doesn't really matter so much. At some point, you're going to block so much light, of course, you're going to get less average current. But this makes perfect sense. Now, if I go back over here, and if I change the current from 35 milliamp to, let's say, 30 milliamp, we are right at the exponential part of this laser diode. If I go back, you can see that we've lost quite a bit of these stray currents. So it went from about 4.5 nanoamp to 1.5 nanoamp, even though we only changed the current by a small percentage. So this is all very consistent with exactly what you would expect this to be. But this combination of having lock-in with external references and controlling your own DC sources and mixing and matching of modes of operation between these remote modules is a really attractive solution. I had several other experiments that I wanted to show you. For example, using this miniaturized Stirling engine to go down to 77 Kelvin, and then taking advantage of the Lakeshore silicon diodes to make cryogenic measurements in lock-in mode. I was using some Hall effect sensors to measure the magnetic flux leakage of various relays and see how they can affect nearby electronics. Now, this length of this video is really getting out of control, so I have to save these for some future videos. I'm just having too much fun with this device. But I hope you can appreciate some of the really critical capabilities of this M81 system. Lakeshore also publishes a lot of different application notes. In this case, an example of how you can make measurements on a material that has a very high contact resistance and how this instrument can help you. I didn't repeat these measurements because these are really well described and explained, but definitely check out their website for additional types of experiments you can do with this. Now, ultimately, for an instrument like this, the built-in firmware is pretty important because it's going to define how much use you can get out of this directly out of the box. And I hope that they implement some of the functions I mentioned during the review directly built into the unit. One additional piece of hardware that will be very useful is imagine a box roughly the size of one of these with many BNCs on it that allows you to do a matrix. And you can connect that box to any of these source and measure units and then distribute many different points of measurement and multiplex them into these units. And because it's synchronized directly from this device, you can then even do lock-in across many different channels. That would be a pretty useful addition to this entire system. I know that they also have, of course, a source and measure one that I don't have here, but that would be a nice one. In terms of hardware, I think they're going to evolve many different kinds of these interfaces eventually over the long run because you can push the dynamic range around and add other features to it. But it's a really nice start. And there you have it. I hope you enjoyed this extensive review of the Lakeshore M81 system. These reviews take a tremendous amount of effort, but I really want to do justice, especially to instruments that really want to take things to the next step and there's innovations and interesting ideas built into them. As always, if you like it, let me know and let the manufacturer know that you like the review. I get no benefit at all from the sale of these. I really also want to make sure that the reviews have an educational aspect to them. So even if you're not interested in purchasing these equipment, that you learn something in the process of understanding how it works and how to do various metrology measurements. So let me know what you think in the comment section, and I'll see you next time.